How's that? Can you see
Perfect.
me now?
Perfect. Yep. You're
Okay,
on.
thank you. Thank you very much. My name's Marshall Goldberg, and I'm a senior product manager at Lattice Semiconductor. And we're very pleased to be here today to discuss our participation in this project, along with our esteemed colleagues at NSP, Broadcom, and many other fantastic companies. So I'd like to explain to you a new chiplet design we have and how it contributes to the security of the ODSA program. So the new chiplet that we're developing now provides platform firmware resiliency, or PFR, and this protects the firmware of a system against malware, supply chain attacks, and other attacks, even before a system or a circuit board is assembled, before a system boots, while it's in a cold state, while it's booting, and while it's operating, which is a very tall order indeed. So platform firmware resiliency is defined and specified in a NIST special publication 800-193, and its purpose is to ensure that firmware is authenticated before the system boots, before a single line of code loads, and throughout system operation. So the basic mantra, if you will, of PFR is protect, detect, and recover. I want to speak mostly about PFR and security in general. So I'll have to describe our IC just a little bit. So we have PFR compliant FPGAs. So this starts with an FPGA that has on-die dual boot flash memory, and then that flash memory is both authenticated and encrypted. So the bootloader of the FPGA will ensure the integrity of its own image before it boots up. Then once it starts, we'll show you the rest of it. But in addition to that, it has programmable fabric, and you are able to lock all of the IOs on the part, either permanently, like in the case of JTAG, if you wish, or on a temporary basis, and you can unlock it in your configuration bit stream later if you choose. So to simplify the development of a PFR solution, we have a development platform we call the Sentry, and this is comprised of IP blocks which have specially hardened IOs for monitoring I2C traffic and SPI traffic, as well as performing the pre-boot authentication. So you can see in this block diagram how this is all laid out. So there's a RISC-V CPU, that's all in soft fabric. And then there's a special I2C IP and QSPI streamer and monitoring IP, as well as what we call a PLD interface. And what that does is it lets you create your own logic inside of the FPGA, and that there's a mailbox interface. So for example, if you have logic which will execute after authentication completes, for instance, you can receive messages from the C code that executes inside this RISC CPU. So what's really cool about this is that a developer can implement a system like this without any FPGA design experience at all. We have a tool which we call Lattice Propel, and using Propel, you can choose how many of these IPs you want to lay out in your design. So for example, if you're protecting 2 QSPI interfaces, you can lay out 2. If you want to protect 3, you can lay out 3, and you can choose where their pinouts will be on the chip so that you can simplify board design and layout. But the configuration is done using the C programming language. So we provide the C reference code, and using the Propel tool, you can modify and debug and test that code to see how it's going to operate in a real environment, and then you can load it onto a development board. And so we think this is a great improvement to speed up security substantially. So what happens on a system in PFR looks sort of like this, which you see here. So at the bottom, so here's a basic block diagram of a computing system, right? So you have a CPU, you have you have a management MCU, and other types of logic, maybe a disk drive controller, network controller. Those ICs boot from firmware, typically from a SPI flash or similar. So we're not talking about the operating system. We're talking about the firmware of the platform itself. If that platform firmware is hacked, your operating system most likely can't detect the hack, right? Because this is below the surface, and such malware can mask itself so that the operating system can't necessarily tell that the firmware has been hacked. So what happened? So the way we design this is the management FPGA, which is this Lattice part, will hold the protected chips in reset. So a system boots up, we're holding these chips in reset, then we're going to cryptographically authenticate the firmware. So we have the public keys on the die of our chip, right? We have those public keys. We're going to read it, perform a SHA hash, cryptographically authenticate that it's valid. Then we're going to release reset to the protected chip, and it'll boot from that firmware. If the firmware is invalid, we'll replace it with the last known good copy, make sure that that's authentic. And then we can continually monitor the interface to protect against attacks and have nanosecond response time to any illegal instruction that's executed over the I2C or the SPI bus. And you can define what those are on a whitelist or blacklist basis. So this is the basis of PFR. So we designed a reference board, of course, and we sell this to customers of all sorts. And so the way the reference board works is the Lattice MoC-X03, the Lattice FPGA is sort of in the middle here, and it's protecting two FPGAs. And of course, we chose FPGAs because we make them. So in our development system, their FPGA is called the ECP5, which simulate a PCH, a PCH and a BMC chip, right? And so you can go back to that development tool, Propel, modify it. You can download the code to this board and then attack it and test it and make sure it works, make sure the customizations you need work and so forth. So that's great. It's available today, but that doesn't work for ODSA. So for ODSA, we developed a chiplet, and or we're in the process of developing this new chiplet. This is our second chiplet design. So in this design, we took the reference design and we split it onto two boards. Being cheap, it's just one board design, and you can jumper it to act as basically the left half or the right half. And there's a reason for that. So as you saw before, here's the Lattice chiplet on the Lattice IC on the PChiplet A board, and it's protecting an ECP5 FPGA. That's great. Okay, and then the PChiplet B board is in what we call configuration 1, a different configuration. So the Lattice FPGA doesn't protect the ECP5. Instead, the protection is provided over the bus across the board, right? And so what's great about this is you can replace the PChiplet B board with your own board, right? And you can and then we can test PFR protection over the chiplet interface from one board to another. We could even support a third chip on a third board if we wanted to with this design. So this board is being laid out now, and we expect to be able to demonstrate it in Q1 when we next meet together. Now, there's one last thing I wanted to tell you about, and that is when you have this kind of a secure IC, our IC works as a root of trust, right? And it's a programmable root of trust. But in the real world, as we all know, systems are shipped using common carriers. Chips are sold through ordinary distribution channels. They go on boats, they're in trucks, they're shipped by UPS, FedEx, whatever. There are all kinds of places in the world where chips, components, boards can be attacked, right? Particularly as they travel through foreign countries, through third-party assembly houses. We don't really have that much control. So we have developed a system called Supply Guard. And what we do with Supply Guard is we create a custom part number for each customer. And when we manufacture the chip, we program it with a bit stream, which fully locks the chip down. And the only thing that will unlock the IOs and the programming capability of the chip is a bit stream which has been encrypted and signed using a cryptographic key, which we generate on a high security module. And that cryptographic key is known only to the intended customer. It's encrypted using a public key and sent only to that customer. So when our customer, maybe you, develops the bit stream, they're going to encrypt and sign it using a key available only to them. So that bit stream is now encrypted. It can be transmitted to any production facility, and it can't be loaded onto any FPGA. It can't be disassembled, right, or decrypted, except inside of the chips which are provisioned specifically for them. So we have a locked chip that can only be unlocked by code developed by the customer, and the code that the customer develops can only be unlocked inside of a chip that's intended for them. And that unlocking occurs in the assembly house or at the contract manufacturer when the bit stream is programmed onto the chip using a standard bulk programming tool. So during bulk programming, our chip acts essentially as an HSM to cryptographically transfer ownership over to the new bit stream and all of the security credentials contained within it. So in that way, we can create trust from the instant the chips are manufactured throughout the supply chain at the component level. And then the additional components of your system will be cryptographically protected by the Lattice chip, which has been programmed with public keys, which again, you provide and are provisioned onto the chip during the contract manufacturing phase. This ownership can be transferred subsequently using cryptographic credentials under your own control. So this provides protections. You can see from the components the instant they're manufactured throughout all the supply chain, before your system even boots up, and throughout its lifetime all the way to end of life. So